Okay, let's start 3.3. So statements with multiple quantifiers. So basically, you're going to have statements that have a for all and then an exist, or there exists and then an all. 3.2 is just one or the other, but this time you'll have combinations. So let's go through how to interpret statements with two different quantifiers. If you want to establish the truth of a statement of, let's see here, sorry, of this form, for all x and d, there exists a y and e such that p of x. So all x is in d, so you can choose any x, but there has to be only one y. That's what this is saying. So in plain English, your challenge is to allow someone else to pick whatever x element in d they wish, and then you must find an element y in e that works for that x. So basically, they can choose any x, but there's only one specific y that works. Now, if you want to establish the truth of a statement of this form, the other way around, there exists an x and d such that for all y and e, p of xy. So your job is to find, one second. Find one particular x and d that will work no matter what y and e. What y is chosen, basically. What y and e anyone might choose to challenge you with. So there's a specific x, so this is kind of like fixed, and then the y can be chosen by anyone for any element in e. Okay. So let's start off with translations. So translate the following from informal to formal. So we've done this already, but we're going to do it with statements that have multiple quantifiers. So this statement is true. The reciprocal of a real number a is a real number b such that a times b is equal to 1. So this is a true statement. So now, using that information, every non-real zero or every non-zero real number has a reciprocal. Okay, so how do we translate this? So here's every, that's an absolute quantifier, right? So you would say for all non-zero real numbers, we can use x, I guess, don't really matter, or the book uses u, doesn't matter. So for all non-real numbers, u. Okay, so this is the first part, has a reciprocal. So this is kind of saying there's only one. There exists a real number v such that u times v is equal to 1. So every non-real zero, that's for all, has a reciprocal, exists. Okay, so that's how you translate these. So you have to just pay attention, like, okay, is there an absolute statement in there? Is there an existence type, etc.? All right, let's do another one. Part B. Question is, there is a real number with no reciprocal. Okay, so what is my answer here? So there is a real number. So there exists a real number with no reciprocal. So there is none whatsoever. Okay, so the solution means it would be translated this way. There exists a real number We'll use U again. Nah, book uses C. Let's use C, I guess. There exists a real number C such that for all real numbers D, C times D is not equal to 1. Right, because this means no reciprocal. This means reciprocal, right? According to the first part. So there is a real number. There exists a real number, C, with no reciprocal. So for all, since there's none, so for all real numbers D, there is no reciprocals. That's what this is saying. Okay, so that's the first one. Let's do another one. Okay, so the next example, we're going to review the definition of a limit of a sequence. So if you've taken calculus, this should be familiar, although even when you're in there, this definition is a little confusing until you visualize it. So the definition of a sequence studied in calculus uses both quantifiers. Oops, one moment. Okay, sorry. Where was I? So the definition of limit of a sequence studied in calculus uses both quantifiers. For all and there exist, but they also use an if then. So it's a long, complicated definition, as we can see. We say that the limit of a sequence, a sub n, as n goes to infinity, equals L. And we write it this way. The limit of an as n approaches infinity is equal to L. If and only if the value of an becomes arbitrarily close to L, as n gets larger and larger without bound. More precisely, this means that given any positive number epsilon, we can find an integer n such that whenever n is larger, lowercase n, than n, the number a sub n sits between L minus epsilon and L plus epsilon on the number line. Okay, so there's a lot going on here. So let's see here. So it says, let me see, for any epsilon, any positive epsilon. Yeah, positive number epsilon. So let's underline this guy so you can start answering the question. Any, meaning, so that means we should use the for all. So symbolically, we should say for all epsilon greater than 0. Let's keep going. We can find an integer n. So that means an integer n. That means there exists an integer n such that whenever n is larger than n, whenever, meaning for all, there we go. For all ever n, yeah. For all n, I guess I'll make sure it's at least noted that it is an integer for all integer n's. Okay. The number an sits between L minus epsilon and L plus epsilon on the number line. Okay. Gotta be careful here. For all n is larger than n, so I need to make sure I mention that. N is larger than n. And then do the next piece. If then, right? Okay. Let's read this carefully because we said we have a for all and then exists. So we need the if then statement. So where is the if then? Read this again. You can find an integer n such that whenever n is larger than n, the number an sits between L minus epsilon, L plus epsilon. So the if isn't written. Let's look at the question again. Make sure I didn't not write it or something. No, so it's implied. So we kind of have to read it. The number an sits between. So if this is true, then this is true. So if, here we go. If n is greater than n, then the next part is true. Okay. So as you can see, symbolically, it seems a lot more compact, but there's a lot of details in this definition. So one more time, a positive number epsilon, any positive numbers, I need to make sure that's underlined. That means for all epsilon greater than 0, we can find an integer. So that means there's only one, there exists an integer, such that whenever is implying the if part. So whenever n is larger than n, then the following is true. So if this is happening, then this is happening. There we go. Sorry, that was a lot to digest. Forgive me if that was a little confusing, but once you start to see it, it starts to make sense. So piece by piece, okay? Let's move on to the next definition. This is for negating statements with two different quantifiers. So for all x and d, there exists a y and e such that p of xy. So negate everything in here. There exists an x and d such that for all y and e, not p of xy. So this is how you do this negation. And then the opposite direction is pretty much the same. You just swap these quantifiers here. All right, so let's practice that with actual words. So write the negation of the following and determine which is true, the given statement or its negation. Okay, so for every square x, there is a circle y such that x and y have the same color. Okay. Okay, so for every square x, there is a circle y such that x and y have the same color. Okay, so symbolically, right? That is saying for all x, let's see how I can phrase this. It doesn't sound weird. Sorry about that. Got distracted. So for all x, let's just say squares, even though it sounds strange. For all x squares, there exists a y circle such that x and y have the same color. So this is just the straight up translation. The negation of this, right, is what they want to know. The negation, the answer would be there exists, right, negate the square. There exists a square, if you prefer writing it this way, a square x such that for all circles y, x and y do not have the same color. Yeah, so use negate this guy, square, all squares to exist a square, exist a y into all circles, right? Exist a circle into all circles. The circle, yeah. Such that, so this is the p of x part, right? Remember how we said we negate the p of x. So this becomes not p of x, does not have the same color. Okay, let's do part B. There is a triangle x such that for every square y, x is to the right of y. Okay, so there's a triangle x such that for every square y, x is to the right of y. Okay. So there is a triangle. So that means, so the original translation is there exists a triangle X such that for every square, so for all y squares, so for all squares y, either way, try to make it sound normal. For all squares y, x is to the right of y. So now let's do the negation. So this become for all, this become there exists, and then we'll say is not to the right. So that's all we gotta do. So for all triangles, this is my answer. For all triangles X such that one second. Such that there exists a square y that is not to no, let's just phrase that better. Where x is not to the right of y. That sounds better. It's gotta take our time here. It's not difficult. We just want to make it, I just don't want it to sound like strange English, that's all. Doesn't mean it's wrong. Just trying to be proper, where x is not to the right of y. Okay, that's the last, that's all for this example. Let's see if there's another one we can do before we go to 3-4. I guess that's it for 3-3 now that I've checked. So this will be your homework. I'm gonna post this in just a moment. Let's start 3.4.